Okay, so hello everyone and welcome to ACG 2025 day 2, and we are now going to have our session 3, the LLM session. So in this session, we will have 3 papers. The first paper is enhancing cost-effective LLMs with RL for multi-turn text environment. Will be presented by Hanhua Zhu. And are you here?
Yeah, I'm here.
Yeah, sure. So you can please go ahead.
Yeah. So could you guys see my
Sure,
presentation well?
sure.
Yeah. Okay. Then yeah, I will start. Good morning and good afternoon, everyone. My name is Hanhua Zhu, and I'm from Free Corporation and the University of Tokyo. Today, I'm excited to share our work called Enhancing Cost-Effective Large Language Models with Reinforcement Learning for Multi-turn Text-Based Environments. In this talk, I will introduce how we use reinforcement to make cost-efficient large language models perform close to GPT-4, especially in multi-turn environments. And let me start with a brief overview of today's presentation. The goal of our work is to enhance the multi-turn reasoning ability of cost-effective language model while keeping their low computational cost. We use a reinforcement learning-based controller that dynamically selects state-dependent instructions for fixed ALM, which allows adaptive prompting without any model fine-tuning. The results shows our proposed methods achieves performance comparable to GPT-4 in both text word and web shop tasks, while remaining about 17 times more cost efficient. So in recent year, ARM have made remarkable progress and have shown impressive abilities in multi-turn conversations. During multi-turn conversations, the ARM engages in interactive question-answer exchanges and maintaining context across turns to achieve meaningful and consistent conversations. Similarly, when we have an ARM playing a text-based game, the model interacts with a simulated environment, interprets textual observations, and produce sequential actions to achieve game objectives. Both processes share a common multi-turn loop, observation, response, and feedback. This similarity makes text-based games an excellent testbed for starting and improving multi-turn reasoning in language models. Here is an example of GPT-4 playing a text-based game called Text Word. As shown on the right side, the agent receives a textual observation from the environment and generates textual actions in response. A reward is then returned to the agent following the standard reinforcement learning loop. However, current ARM still face several challenges in multi-chain environments. First, the complex interactions. ARM must gather information, clarify goals, and refine responses, which is difficult to manage. Second, maintaining reasoning over long interactions is hard. As the conversation extends, models often lose context and fail to link reasoning across turns. Third, we face prompt length explosion. Handling long interaction histories requires extremely detailed prompts, which become inefficient and expensive. To better understand these limitations, let's look at how different models behave in such setting. Let's compare two representative models, GPT-4 and GPT-3.5. High-performance models like GPT-4 have strong reasoning ability and can handle long, complex prompts, but they come with very high computational costs, makes them impractical for repeated or large-scale use. In contrast, GPT-3.5 is about 30 times cheaper per token and much faster, but it often loses context and struggles with complex reasoning. Here we can see how two models behave in the text world under the same prompts. On the left, The GPT-4 can understand the feedback from the environment and correct its own mistakes. While on the right side, the GPT 3.5 ignores the feedback and just keeps moving forward on its own. This performance cost gap raise an important question. Can we make more cost-efficient LLM behave smartly like high-performance LLM? Before introducing our method, let's quickly review the two main existing approaches. First, prompt-based methods such as chain of thought, react, reflection, and adapt. They guide the model through carefully crafted prompts, but these prompts become extremely long in multi-turn settings, leading to high token costs and depend on manual design. Second, fine-tuning based methods, including full fine-tuning or lightweight adapters like LoRa. They can improve reasoning performance but require large-scale data, GPU resources, and continuous maintenance. Both methods have limitations, which motivates our new lightweight approach based on reinforcement learning. To address these challenges, we propose an reinforcement learning enhanced framework that improves cost-efficient LLM without updating their parameters. Our system consists of two main components. The first one, a controller trained with reinforcement learning, which selects the most appropriate instruction at each step based on the current observation and history. The second one, a frozen LLM, which generates the next action by combining that instruction with the current states. The controller learns its policy from environments, rewards, dynamically adapting to context and maintaining reasoning continuities. This design directly solves our previous challenges, handling complex interactions and maintaining reasoning over long terms through dynamic control and reducing costs by improving the performance of cost-efficient LLM. This is the overall architecture. At each step, the environment provides a textual state, including the current observation and the history. Then the embedding encoder converts it into a vector, and the instructor produces a probability distribution over possible instructions. The chosen instruction is concatenated with the current state and task prompt, then passed to the frozen LLM, which outputs an action. And this action is executed in the environment, producing the next observation as a reward. We evaluated our method in two well-known multi-turn text-based environments, TextWorld and WebShop. Both tasks require multiple steps of reasoning and planning. In TextWorld, the agent navigates and finding objects in a house. In WebShop, it must search, select, and purchase items according to a user instruction. And let's look at them one by one. In TextWorld, we use the simplified version where the goal consists of 4 subtasks: finding the key, unlocking the door, finding the target item, and placing it in the correct location. The controller chooses among 5 possible instructions, such as find the old key or use correct verbs. This is an example showing how a selected instruction changes the behavior of GPT 3.5. By aiding appropriate advice, GPT 3.5 fixes its action with correct verb. Here are the results from the text world. In the training environment, our methods, the green one, achieved a score close to GPT-4, the origin one, while the vanilla GPT 3.5, the blue one, stays much lower. In the test environments shown below, generated from different random seeds with new item locations, room descriptions, and navigation instructions, GPT-4 again achieved the best performers. However, our proposed method performed better than the original GPT 3.5 in 4 out of 5 test cases, and in the remaining cases, the gap was very small. These results highlight that our method generalized well across on-scene environments. Next, we evaluated our method in WebShop, a large-scale simulated e-commercial environment. The task can be divided into three main subtasks: search, selection, and customization. Where the agent searches for a product, selects the most appropriate item, and customizes its options such as color or size, and finally purchase the item. As shown on the right, our controller chooses not only which instruction to use at each step, but also which LLM to call, either the base GPT 3.5 or the expert GPT 4. And the controller can re-execute previous subtask if necessary. The controller learns when to invoke the expert model for difficult cases and when to stay with the cheaper base model to reduce cost. This setup allows the agent to balance accuracy and cost, achieving better tasking performance while remaining cost efficient. Here are the results from the web shop environment. Our method achieved a success rate of 37%, which is higher than vanilla GPT 3.5 and even slightly outperformed GPT 4. This improvement comes from the IR controller, which learns better subtasking execution and provides more appropriate advice at each step. Which interesting is that the expert model GPT-4 was used in only about 5% of the steps, and re-execution occurred in less than 4% of cases. Even with such limited expert use, if we remove the expert option, the success rate will decrease from 37% to 32%, showing that the expert model provides valuable guidance when invoking it. However, due to its limited selection frequency, further analysis is needed to understand when and why this benefit occurs. Finally, let's look at the cost analysis. As we know, GPT-4 is much more expensive to use, while GPT 3.5 is about 30 times cheaper. In the text world environment, even though GPT 3.5 usually needs more turn to finish a task, its overall cost remains around 17 times lower than GPT-4. Our method introduced only a very small overhead, mainly from the controller's instruction prefix. So we are able to keep the cost almost as low as GPT 3.5 while still achieving performance close to GPT-4. To summarize our contributions, we propose a reinforcement learning-based framework to enhance cost-efficient LLMs like GPT 3.5 in multi-turn environments. We introduce state-dependent instruction selection, enabling the adaptive prompting without fine-tuning. We demonstrate that our proposed method can bridge performance gap to GPT-4, achieving comparable results in text world and web shop, while keeping costs very low. As for future work, we plan to test this framework in more complex environments, develop the methods for automatic instruction generation, and design scalable controller for broader real-world applications. And that's all. Thank you.
Yeah, and thank you for the talk. And now we open for some questions. And you can use a QA or the chat to ask some questions. Well, I see there's no questions now. So maybe let me ask several questions first. And I want to ask about the instruction. So in this work, you select the instruction manually or by some other method?
You mean instructions? The instruction
yeah,
here?
this instruction set. Yeah.
In this work, I design the instruction manually, and in the future work, I plan to do something like the automatic generation.
Okay, so the next question is for the instruction, because you have to let the controller to learn to choose the instruction for each state. So how do you generate the data, generate the training data for each state and instruction?
Yeah, because I trained the model with reinforcement learning, so I have the environment, and let the controller the model to self-collect the data when he
Okay.
yeah,
So
using the
if the
PPO, yeah.
model selects some wrong instruction, you will get bad reward.
Yeah.
Or okay, okay. Yeah.
So,
Mhm. And another question is about you say that you are planning to make this framework to more complex text environment in the
yeah.
future world. But currently, it seems that the computation cost of the controller is not big. It's really small, as
Yeah.
you mentioned here. But if you extend this work to possibly more complex environment, will the computation cost be still minor, or it can be larger and can be a big overhead? Or what do you
Oh
think about
yeah.
this issue?
Yeah, I think that's a very interesting questions. Because in the real world, use of ARM, if you are using something like the cloud or ChatGPT, you need to care about the limitation of the cost and the token limitation. And one idea of this, one motivation of this research is to just, if you use the ChatGPT 4, it's a very, powerful model. You can get a very good result in the real world task, but it will cost you a lot of money. And here it's a really, uh, here the cost is not too high because it's a totally simple task. But if you want to, for the real world service, you need to handle millions of interactions every day or not. And if you compute with really, millions times of uh, calling ChatGPT 4, it will be a very expensive money. So at that time, if you could just use the GPT 3.5, and you will get a much lower cost. And I think that is something like the the contribution of this work, and where we can apply this work in the real world task.
Yeah, all right. So we also have another question in
Yeah.
QA. Yeah, can you easily integrate newer versions like ChatGPT 5, or do you think newer versions will change anything about efficiency and or cost?
Yeah, yeah, that needs further experiments, I think, yeah. Because the ChatGPT 5 is powerful and also cheaper than before. But I'm still
Mhm.
wondering that when I use GPT-5 by my own, sometimes I think it's not so powerful than GPT for the generated answer. I think there's something trade-off between these two models, and I think I need more experiment to prove that if this method is useful for the ChatGPT 5 or it's only useful for the ChatGPT 3.5. Yeah.
All right. Thank you very much. So if you have further questions, you can still use the QA and the chat. And let's go to the second paper in real-time expert choice commentary using LLM. The presenter should be Paul Ciancarini. Are you here? Yeah.
Yes, good morning.
So please go ahead. Thank you very much.
Share the screen. So this is a joint work with my student Marat Gubaidullin, who is present, connected. He should be the presenter, but he is ill, so I will talk instead of him. And also with Andrea Manzo. I am from University of Bologna, and Marat is from Innopolis University. This work has the goal to test the ability of large to test and increase the ability of large language models to comment a chess game, especially in real time, while it is applied, for instance, on any site and show it. We want to see if a language model can help in understanding what's happening on the chessboard. To do this, we enrich the rhetoric, the storytelling of the language model using an external service that is basically a chess engine. We use Stockfish. However, we use Stockfish, the Windrow losing model, in which we apply what it is known as a theory of chess as a complex system. It was introduced by Alexander Shashin, who is a Russian physician and chess coach. He wrote a book that I will mention and helps in improving in our experience, in our opinion, helps improving the rhetoric of a language model when commenting a chess game. So I will describe shortly the architecture of the system that is called Ciancarini, and we will also talk a little bit about the evaluation that we performed. So what is the Ciancarini theory? Ciancarini theory is explained in this book titled Best Play, a new method for discovering the strongest move. It is a chess book. It's not a scientific book. However, there is an initial part in which the Alexander Shashin presents chess as a mathematical description of a complex system that is used to single out, to find out what he calls the style or the mood of the position. The mood is labeled with the name of three well-known chess champions like Mikhail Tal, Raul Capablanca, and Petrosian, Tigran Petrosian. Tal was a master of attack, Capablanca a master of strategy, and Petrosian a master of defense. And so the idea of labeling in this way a position means that, for instance, if you label Petrosian, means that you are in a disadvantage and you should find out the defense. And we use this idea to enrich the storytelling of a position. Basically, the Ciancarini theory is based on 5 factors that are basically mathematical parts of a normal chess polynomial that was used before the era of neural networks. So we can use these factors, mathematical factors, I repeat, to evaluate the position. And this is very similar to a combined polynomial evaluation. So for instance, the material is obtained by the ratio of material white over material of black. And kings are not counted, of course, and this is a very classic counting. Time represents the mobility of all the pieces of the first and second player. Then there is safety of the king. This is also usual. Curiously, Shashin gave no computing way for these factors, so we had to invent an implementation for king safety. So in our case, it represents the total number of attacking moves on an enemy king, and it's neighboring squares by the first and second players. Then there is a compactness, that is the number of kings and pawns of the players, and it is the area in which you restrict the king and you try to understand how well the king is defended by the pawns and other pieces. This is called compactness. And instead, this is expansion, that is the sum of the rank numbers of the pieces, and n is the number of the pieces. And so it gives an idea of how of mass according to the Shashin terminology. So this is the overall description of the mathematics of chess according to this theory that I repeat. I'm not going into details, but if you check the book, it is explained how you can exploit this to evaluate the mood of a position. So in which way we exploit this? Basically, we exploit the idea that the mathematical output of a search engine enriched with the labeling of the position according to Tal, Capablanca, Petrosian, and other numerical evaluations that you can extract from a chess engine like Stockfish, you build, in our case, a microservice, including some ingestion input service, some output service that contains the main logic. There's an AI commentator in Python which is able to talk with a language model, and finally a display, free service written in Go and one in Python. And the architecture is basically the input via a graphical interface. You can input either a fan description of the position, a sun description of the position, or and then you use a move analyzer, a chess engine, like for instance Stockfish, to get data by which you can feed the model, and then you extract the response and you broadcast to the display and to all people connected to this system. So these are some videos which show the way in which we have realized Ciancarini. This is the input window. The output receives the most from the input and calls the engine, the most analyzer, and this gets some evaluation, including the best move, the principal variation, the VDL evaluation. VDL stands for win, draw, lose evaluation, that was introduced by Lela and is now built inside Stockfish, and also the evaluation of the Shashin area. So it is just a mathematical evaluation without any comments. The output module receives the most from the engine and is able to talk about the position, even if basically we do not pass the position to the model, to the language model, but only the numerical evaluation. These numerical evaluations are used inside the model to talk about the state of the game. And so the output receives the tagged moves from the Shashin analyzer. By the way, we can use Stockfish, but also some other engine, insofar as we get the information from the engine that can be useful to feed the language model. So we build a prompt based on the tags that we get from the engine, and we send a prompt to the AI commentator service, and this receives the response, the formats, and the display service. And so we get something like this, in which there is a description of full description of the position as input by the user, and the output from the engine with some evaluation in terms of numerical evaluation of possible moves and variations. And then we add the comments as output by the language model, like in this case, we get this kind of rhetoric because the prompt fired this kind of rhetoric. I will show you. In the paper, you find a more complex example taken from a classic game between Petrosian and Botvinnik in 1951. And you see how long the comment that we can module using the prompt. The prompt themselves, in this case, we have two examples. On the left, you see the prompt without using Shashin. I can try to single out Shashin comments are in this case here. And we use the position style. In this case, it is deep strategic defense, so it is a Capablanca-like. And we suggest the model to use this information, that is just a label, after all, to set a narrative tone. Instead, here, there is just a suggestion on the prompt that asks for just a maximum number of symbols, never reveal the scores in terms of numeric evaluation, just if there is a possibility of checkmate. Then the context as obtained from the engine. So the move that is applied, the best engine move selected by the engine, the trend we try to find out what is the trend of the evaluation from the engine, the best evaluation, the information about the players, and that's it. And with a few guidelines, just to, in this case, if the applied move equals the best move, you can place, or conclude with a forward-looking hook. Let's see if something like a very standard comment. Instead, in the other prompt, we have a more complex interaction required. This part is very similar, is basically the same. Also, this is the same. However, the guidelines are richer, and we have some more use of the Shashin information concerning the style of the position. We evaluated the system in a very simple way. We asked to some players about the quality of the comments with and without Shashin theory. And we gave them 8 positions and the comments from the system. So 8 positions, we asked a number of people to check the comments, and we recorded the votes, trying to have at least 50 votes per position. This is the distribution of the elo strength of the voter. So most were very quite weak. A few were very strong, and with a number of people in the middle. And what we got is that according to the model that we were able to use these 4 different models: ChatGPT 4o, ChatGPT 04 mini, DeepSeek Reasoning 1, and CloudSonnet 4. And we found out that with the Shashin prompt, the best, if I understand well, I repeat, I was not completely prepared for this presentation, but according the table, this should be the best result. For sure, there is a clear improvement in both values between the two, without using Shashin. I repeat, in our case, Shashin is used especially for the rhetoric. We have also, sorry for this, another table that reports the Welsh test, and also here you get good improvement of the results. Finally, there is a clear improvement in the reported evaluation by the humans of the comments we have summarized in this diagram. So basically, we can summarize as a 36% improvement using just the Shashin tag. The improvement strongly depends, so it is a form of benchmarking that we can pretend that chess comments induces on language models. In our selected models, we get up to almost 50% of improvement. Shashintari, if I remember well, is open source and is available. And it's intended, the usage is for real-time live chess games. However, of course, it's also very interesting to use a system like this for post-mortem analysis. But clearly, we plan to work much more on this. This was a master thesis, basically, that I am presenting here. But we are planning to invest more on this kind of systems because we believe they are very useful in several situations, in chess tournaments and so on. Okay. The reference list are especially concerning. There are several papers which even before the era of language models, which tried to develop chess commenters. Actually, this is a very old problem that I found traced already 40 years ago in some papers by Milne. And I also remember that the ACG gave a prize for the best commenting program, say 25 years ago, I think. But now, of course, with the technology or language models, we have a completely new approach to this kind of problem. Thank you for listening.
Yeah, thank you very much. So, let's see any questions?
So another question. First of all, do you understand me?
Yes, I listen to you. I hear.
Sorry. Yes, yes. Compliments for your, I would say, overview and also for your diving into the history. I remember quite well that the idea for the best commenting program that was by Bob Hasberg. And then we thought we should do that. And so we started with programming this idea, at least, but it was by far not in the way you now said. But now I have a big, difficult question, yes, and it complains two things. That is, how far is, I would say, according to your analysis or the program's analysis, we are distinct from perfect chess. That means for endgames, for 7 endgames, we know that. Yes, for endgames with 7 pieces, I would say. We know that. And so have you also tested your program with, I would say, the perfect knowledge?
Yeah, this is an interesting question. Well, in this research, I would say I'm not, I talk for myself. I'm not
Yes.
studying perfect chess. For sure, what I discovered is that chess engines are not perfect in the sense that we are used to have some output from chess engine that is useful for storytelling by language models, but is not enough. So what I'm doing in concerning perfection, we are trying to improve the output of chess engines, meaning adding information that usually is not output. We want to know some more mathematical information, so to speak, that you can get from chess engines that usually is not output. With this information, we try to improve, if you want to make perfect, the comments, but not the game. The second question is interesting. I imagine that you allude to endings. In endings, we know that we have perfect play, especially if you exploit table-based or databases of positions. Well, this is an interesting question. I admit that we have not used this to comment the table base, but for sure it is something important because for sure we want to know when the ending is playable perfectly, but this information again must be extracted either by the chess engine that probably knows that now we are in so to speak, a perfect position with a perfect ending. But this is usually not easily extracted. You cannot get this information easily from the chess engine. And so again, we are trying fine-tuning of the models to feed the information that they are talking about a special position in which you can have a perfect play. But for sure, I think it is the task of the engine to offer this kind of information. This is a good example of the kind of information that there is some perfect play ongoing that is not easy to get from the engine. But you have to flag
Yes.
this information.
Yes, I was also if there are other questions, then I give the floor to other persons, so that is fine. But if there are no other questions, then I continue. So, Mr. Chairman, it is up to you to make a decision.
Yeah. Sorry, can you repeat the question, please? If any, you have a question, Jap?
Yeah, I have a question, but I give the floor. If there are other persons with questions, then I give them the preference for the chairman.
Yeah, there's a question in the QA. Yeah, and how robust is the system against illegal moves? And how does the system behave if you tell it that one player play an illegal move? Or how do you think it's behaved?
Yes, hello. Can I answer this question?
This is my
Can you hear me?
Go on, Marat. Yes, we can hear you. Go on.
Yes. So the answer is simple. So we can't handle moves. We can't handle illegal moves. If you try to give this program an illegal move, it just says that this move is illegal and can't be played. So nothing is passed to the main logic, and no commentary is provided.
Okay, Mr.
Okay.
Chairman. Then I come up with my last question. Is that possible? Yes, I will be short. You understand me, Paolo?
I can understand the use. Yes.
Okay, then you give, I would say, 5 criteria or 5, I would say, parameters: material, time, safety, compactness, and expansion. Yes. Is it possible that you missed one criterion? And I don't know which criterion, but could you, I would say, make an analysis with the perfect knowledge, the seven piece endgames, etc. Apply these criteria and then look for, I would say, the missing answer, and so find a new criteria.
Absolutely. I want to be clear about that. The Shashin theory is something that we, in some sense, use to improve our understanding of the chess engine output. The chess engine output has a number that is called the WDL evaluation, that is based on machine learning, and it is a prediction of the possible result of the game. We apply the Shashin theory to that evaluation. And in this case, in this way, we have found that is a better production of comments. I don't know if you want to comment as well, Marat, about this. I'm now reading the question, for instance, how robust is the system against illegal moves? They are dealt by the chess engine. How do you think it behaves? I would say that the illegal move is rejected by the user interface, basically. Because we are still using, at least in our implementation that I know, that we use normal user interfaces. Marat, you want to comment about this question?
Yes, I already answered. That's correct. The program just doesn't.
Yeah, you are right. These are the questions that you tried to answer. Yes. Basically, we
Yes.
have a system in which there is the language model for storytelling, a chess engine for chess moves. So the rules of chess are known by the chess engine, not by the model. Okay.
Yeah, thank you very much. So probably we should move to the next talk. Yeah, the next talk is SpinGPT and LLM approach to playing poker correctly. And the presenter is Narada Maugin. Are you here?
Yes.
Okay, so please go ahead. Thank you very much.
Do you see my screen? Yes. Okay, so hello everyone. I'm Narada Maugin, and I'm glad to be there to present a joint work with Tristan Cazenave. It's a work on poker and LLM. actually we developed SpinGPT, a large language model that can play the poker. So first, what is poker? So it's not a game. It's actually it's a family of card games, and the most common variant is No Limit Texas Hold'em, played typically from 2 to 10 players. And there is a part of dealing the cards, and then there is 4 betting rounds called pre-flop, flop, turn, and river. So it originated in the United States in the 1820s, and today it has attracted about 100 million players worldwide. So for us, it's an imperfect information game, just because the players don't know each other's cards, and the game tree is enormous, making it very hard to solve. Okay, so to set the context, I will briefly review a few milestones in poker AI. So of course, it's not exhaustive. So in 2006, the first computer poker competition, ACPC, launched. So it gave researchers a shared benchmark and a place to train their agents to compare their results and to exchange ideas over many years. And the next years, it was very important because it has been introduced the counterfactual regret minimization, CFR algorithm. And CFR became the core of many later agents, like CFUs in 2014. Which solves the heads-up limit. So heads-up means 1v1, and limit just means that the amount of chips one can bet is limited. So this constrained the game size of the game to 10 to the 13th states. But 3 years later, with ideas and improvement from CFR, Librettus pop and solve heads-up no limit this time. So no limit just means the amount of chips one can bet is unlimited. So the game size became enormous, around 10 to the power of 160. And the same team, Braun and Sondholm, published 2 years later Pluribus. This time, it extending strong play in a multiplayer setting because unless it was not in heads-up but in 6-player format. Okay, so what challenge remain for poker AIs? So after that, so the main challenge is clearly tournaments, because in tournaments there is a dynamic evolution. Early on, there are n players who are divided among tables of 6 to 9 players, and then step by step players bust. So the table size and the stack distributions keep changing over time. So this breaks the stationarity that we had with the previous AIs, and that makes standard equilibrium methods like CFR harder to apply. Also, I will not enter in detail, but maximizing chips EV, expected value of chips, is not the right objective in this format. So to make progress, we focus on a simpler problem, Spin and Go. So Spin and Go is a 3-player mini tournament where the winner take all. It's simpler, of course, than tournaments, where there can be thousands of players, but it still captures 2 main tournament dynamics, evolution of players and evolution of stack. So, and it's the most played online format by far. So using LLMs for poker can seem odd because off-the-shelf models played poorly, very badly, even with few short prompts. It's mainly because there is no large data set of poker hands available online, unlike chess, for instance. And so during their pre-training, LLMs don't see many poker hands, and so they are not trained on it. So why use an LLM anyway? It still has its advantages. So first, it already knows some rules and basic strategies, like knowing that a pair of aces is the best possible hand. And crucially, it can learn hand histories from structured text representations. And then output actions after training. And actually, previous studies has shown that fine tuning is very useful for a model to play poker. So, but to fine tune, we need data. And as we said, there is no large open data set containing poker hand histories online. So how did we proceed? We use the fact that I was a former professional poker players to build our own data set from spin and go hands that I played between 2019 and 2020 on high stakes. And so we had a total of 320,000 hands that we used. So a poker hand retrieved from a poker tracker look like this. It's very long and contains a lot of unnecessary information like the dates. So we have to reduce it to retain only the information relevant to decision making. So this is the result here. So there is the position of the player, the amount of chips it have, the amount of opponents' chips, our hand, and the action previous on the pre-flop, on the flop, turn, and river. And then here, each column means that it's a model turn to play. And here, so the expected answer was X, so means for check, a legal poker action. Okay, so with all this 320,000 hands, we were ready for the fine tuning. So we used Llama 3.1 with 8 billions of parameters. So one plus of this model is its open weight. So we can use it almost freely. And it's small enough to be trained on a single GPU. But there is limitation, of course. As we said, it has a beginner level at poker, and it has lower capacities than larger LLMs with their hundreds of billions parameters. And as we know, in this area, quantity matters. So we train it for 10 hours, and we call the resulting model SpinGPT SFT. So SpinGPT SFT. So we evaluate SpinGPT SFT on a 32K test set, and we got 80% of exact accuracy and 84% of tolerance accuracy. So what does it mean? It means that exact accuracy, it's when the model's action token exactly equals the action played when I was a professional here. And accuracy with tolerance is the same, but for bet or raise, when we have a target size, we accept a small deviation between this target size. For instance, if the target size was 2.6, prediction of 2.5 counts as correct. So, okay, and we have 8.4% illegal action. So here as a confusion matrix. So in rows as true labels and columns as a predicted label. So the diagonal gives exact matches. So for instance, if we consider the row check, so where when I play check, 9% of time our model say bet. He never say call. 89% of the time he say check too, and he say once fold and raise 1.7% of time, which are two illegal action. So before the fine-tuning, it was almost 0% accuracy, and now it's way better, but at what point? So we use Slumbot as a 2018 AI World Champion as a convenient heads-up baseline. So it's a common benchmark to play against and to evaluate AIs. But there is a depth mismatch because SpinGPT was trained on short stacks with a low amount of big line of stack, and Slumbot is trained and is able to play at deep stack. So it's a problem because applying, of course, a short stack policy tends to make mistakes at deep stacks, and especially tends to all in, to shove way too often, which produces massive losses. So to control this, we had to patch our model when it goes all in like this. Okay, so this table reports SpinGPT SFT's win rate against Slumbot. Here, the confidence interval and the number of hands played. So the win rate is expressed in BB100. So it's the expected big blind 1 per 100 hands. So what does it mean? When it's negative, that means that we are losing. When it's around 0, that means that it's equal. And when it's positive, that means we are winning. And when it's more than 6, winning a lot. So 13.4 is a good win rate, but there is a huge confidence interval. So we can probably say that SpinGPT SFT wins against Slumbot, but not at what point. To compare, I reported here win rate that other model had against SpinGPT, against Slumbot. Sorry. Okay, so SpinGPT SFT beats Slumbot, but can we do even better? And so far, SpinGPT SFT has been trained only on hands that I played, so I was a professional, but I made, of course, mistakes. And so SpinGPT SFT is trying to imitate a strategy that includes mistakes. We can do better than that. So the idea is to train again our model with synthetic hands from a solver that approximate Nash equilibrium using CFR-like algorithm. And so we use for that InstaGTO, a commercial solver. And this time we use reinforcement learning with ORPO instead of fine-tuning, which allows us to give the best answer in a state, but also the worst. So we train it and we include real hands to prevent catastrophic forgetting. Okay, so we train for 10 hours again, and we obtain our final model, SpinGPT. So on the imitation side, we can see that SpinGPT achieves similar accuracy to SpinGPT SFT, the first version, on the Pro dataset. And on the solver dataset, the amount is slightly lower, of course, because it's way more difficult to imitate solver's policy than humans one. We didn't play SpinGPT against Slumbot because, as we said, the evaluation format is mismatched. And the evaluation require a lot of computations. But we did a match between the two versions, so SpinGPT and SpinGPT SFT, in a convenient format. And we can see that SpinGPT beats by a wide margin SpinGPT SFT, so the reinforcement learning part was effective. Unfortunately, there is some limitations. Main one is that absolute strength of SpinGPT is not clear, is pretty unknown because there is no online Spin and Go bot that we can play against easily, and there is no evaluations against humans. That's something that is planned, and it's really the main the main evaluation for Poker AI. And there is other problem. Of course, there is many improvements that can be done, especially combine LLM with solver. But I will conclude there. So to conclude, we trained SpinGPT in 2 stages: supervised fine-tuning on expert data, then reinforcement learning with SORPO and solver data. The first version beat SlumBot, and the second version outperformed the third version. There is around 80% of time our SpinGPT done the same action than the human and the solver. And as we just said, the benchmark SlumBot is not very convenient, so we have to use to evaluate it versus human. And you can try SpinGPT at this address. Okay, thanks for listening, and I'm happy to take your questions.
Okay, so thank you very much. And well, because we have already exceeded the time, so maybe we have 1 or 2 short questions. Yeah. So, okay, there are questions on the QA. The first one is, you said no evaluation against human. The question, 2 related question is, have you tried yourself and did you win? The second question is, are you allowed to play on commercial website with AI, or is forbidden?
No, it's not possible to play with this AI on the website, on Poker website. It's not allowed. The other question was, can you please recap the training and evaluation? So on the slide 9, I said that it's only the test set. So we trained our model on 320,000 hands, but we divided we take 10% of that on for the test set. I don't think if I understand correctly the question. And what was other questions?
Yeah. Okay, so there's another 2 questions. And can you please recap the training and evaluation? Specifically, you have mentioned that n equals to 32,000 was a training set. And on slide 9, you have written that the test set was also n equals to 32,000. Was it the same set? If yes, why wasn't there a separate test set?
The training set was on this amount of hands, and so it's 10 times bigger than the test set. Of course, it's not the same. Yeah, of course, it's not the same.
Okay, so there's the next question is, thank you for your presentation. What is your opinion Is it possible to use your solution SpinGPT to teach regular intermediates to play poker better?
It's the goal, yes, of course. As we see in the previous presentation, the ability also to comment games could be really interesting. So now we don't goes into that way, but in the future, I think it could be, yes, something very useful. And the second question, can we somehow predict why the model answer and how it's answer, and then to try to explain? It's something very interesting, yes, but it's not something that we go through until now.
So, all right. So probably there's no further questions on QA. No, and any more questions? So if there's participation in this session.
Thank you, Hang, for chairing, and thanks to all the speakers once again.